In this video, we're going to do the last example in our titration calculations. Just remember that after you're done this video, you should take a look at the recap, the titration curve recap, and then do the homework and watch the video on how to do titrations. If you haven't already done so, I'd recommend you watch the pause, try, play situation here. It's a good preview of the problem that we're going to do here together. So that way you can get an idea as to how to do this, and you can try this one on your own before even watching my attempt at it. So let's go ahead and take a look at this example. We have example number 1. If a 200 milliliter solution containing 0.15 molar hydrobromic acid is mixed with 100 ml solution containing 0.20 molar potassium hydroxide, what is the pH of the mixture, the final mixture? So let's take a look at this question carefully. Let's write out a reaction equation first. So we have our hydrobromic acid, HBr, AQ, and that's reacting with potassium hydroxide, KOH, AQ. We're going to, and it's a solution of potassium hydroxide. We're going to do our double displacement. We'll get a salt, which is KBr. That dissolves in water, plus our water. So a typical acid-base reaction. And we're going to write down information. So for the hydrobromic acid, we have volume is 200 mils, which is approximately 0.2 liters. I didn't keep all my sig figs there, but I will. I just keep in mind that this is like having 5 sig figs. I should have written all 5 zeros down there. It's okay if you don't write them all out in the interest of time, but make sure when you're looking at your sig figs, you're looking at the sig figs that you had in the original question. So be careful with that. And our concentration is 0.15 moles per liter. And over here, our volume is 100.0 mils, which is approximately 0.1 liters. Again, same idea. Make sure this counts as 4 sig figs, not 5. I counted wrong there. So 4 sig figs. And our concentration of this over here is 0.20 moles per liter. So that's our information there that's provided to us. I know you're thinking, well, shouldn't the pH be 7 once you mix everything together? Well, theoretically, because this is a strong acid and this is a strong base, the pH you would think should be 7 because you have salt and water. That's what you have on this side here. Okay, but that's only if you've mixed these perfectly together, if you don't have any excess of an acid or excess of a base. And that's what we need to figure out. Do we have any excess here? So firstly, we need to make sure that it's all balanced, because we have to figure out if we have any excess or limiting reactant. And it looks like my equation is balanced. To figure out if you have excess or limiting reactants, you need your number of moles. So let's go ahead and figure out the number of moles for each of these. C times V, which is 0.1, times our 0.2. So it's basically like 0.2 divided by 10. So liters times 0.20 moles per liter, and you get 0.02 moles. Okay. Now, let's do the same thing for here. So N is equal to C times V, which is equal to the 0.15 moles per liter times 0.2 liters. Cancel liters there. So you have 0.2 times 0.15, and we get 0.03 moles. Now, we have to find out which one is the limiting reactant. So determine LR and ER. That's important. We want to see what we're going to have left over. Now, there's a couple ways you can do that. You can use method 1, method 2, method 3. Doesn't really matter. Here we have a 1-to-1 ratio. So technically we could use method 1. The limiting reactant is the one you have less of, and the excess reactant is the one you have more of, because it's a 1-to-1 ratio. You're comparing them nice and evenly there. So since we have a 1-to-1 ratio between HBr and KOH, the LR is KOH. It's KOH because moles of KOH is less than moles of HBr. So what that means is we're going to use up all of our KOH in this reaction. Okay? And the ER is HBr. That's what the ER is. So there's going to be some leftover. There's going to be leftover acid. So therefore, leftover acid, which means that our final pH won't be 7. It'll be less than 7 because we have leftover acid there. We had some excess acid. We have to find out how much leftover acid we had. So step 3, using the LR, determine the leftover excess, which is our acid, HBr. So what do? I use my LR. I do a ratio between my LR and my excess. So I say that my between my LR, so my LR was KOH. So there's a 1 KOH to 1 HBr ratio. So what that means is if I have 0.02 moles of KOH, then I should have, I'm trying to find out how much HBr will react with it. So I do times my ratio there, 1 mole of HBr for every 1 mole of KOH. I should have about 0.02 moles of HBr reacting. That's what I should have, okay? So this is should. Okay. That's what will react, should/will react. Now, how much HBr do I have? I have 0.03. So what that means is to find the leftover, I do have minus what should or will react, which is 0.03 minus 0.02, and I get 0.01 moles of HBr left over. So essentially, once the reaction's done, I have KBr, H2O, no more KOH because that was limiting, but I have some HBr left over. And that's the amount of HBr left over, and that will determine my final pH there, the leftover HBr. If there was leftover base, I'd have to use my leftover base to figure out the pH of the mixture. So what am I going to do now? Well, this is like a regular pH of solution problem. So I have HBr. I'm going to write an ionization equation. So H plus AQ plus Br minus AQ. The reason I'm using HBr is because that's what's left over there, and that's an acid. It'll determine my pH. The other stuff here, this is neutral. This is neutral. This does not have anything to do with my pH right now. It won't make it acidic or basic, so I'm good with that right now. And so I'm going to write down the number of moles I have. I have 0.01 moles of HBr. And since it's a 1 to 1 to 1 ratio, I also have 0.01 moles of H+. Now I want the concentration. Okay, so concentration is equal to N over V, which is equal to my 0.01 moles divided by my volume. So what's my volume here? Like, well, what's my volume of my mixture? Well, you look at what the volume of your mixture is at the end after you've mixed everything together. I have 200 mils plus 100 mils. That's 300.0 mils. So my volume here, volume is equal to 200.0 plus 100.0, which is 300.0 mils, or about 0.3 liters. So divided by 0.3 liters, and I get 0.0333 keeps going, molar or moles per liter. So in this question, it was a neutralization reaction. You would think the pH of the mixture at the end should be 7, but it may not be. It depends if you have excess base or acid. So what I had to do was I had to find out if there was limiting or excess reactant. If there was no limiting or excess reactant, if everything reacted completely with each other, if it was a strong acid, strong base, pH should be equal to 7. And it is a strong acid, strong base titration here, or reaction here. So I had to determine my LR. I found there was a KOH, so it was used up completely. And therefore the ER is the HBr. So that's what's left over. There's some leftover acid there. So we know my pH is going to be less than 7 of the solution in its entirety. I just have to find out how much leftover acid there is. To do that, I said, okay, well, if I have my limiting reactant, which is KOH, that's going to react with this much HBr. I did my mole ratio with the excess and said that's how much HBr will react. But I have more than that because it's my excess. I have 0.03 moles and only 0.02 moles will react. So to find the leftover, I just do what I have minus what will react, and that gives me my leftover HBr. And then I just made an ionization equation to see how many moles of H plus I would have in the solution because it's a strong acid. So I'd have 0.01 moles of H plus. And so using the moles and the volume, I found the concentration. The volume is the volume of the mixture because we're asking you for what the final pH of the mixture is going to be. So it's 100 plus 200, which is 300. So I got that concentration there. Now we asked you for pH. So our last step is pH is equal to the negative log of the H plus concentration. So this is, by the way, this is concentration of H plus. That's what I'm finding there. Okay, so it's going to be negative log of 0.0333, so on and so forth. So let's do that. And I get about 1.477121255 as my pH, which is approximately to the number of sig figs. Let's see, we have, looks like 2 sig figs is our smallest number of sig figs. So we get about 1.5. Therefore, the pH of the final mixture is approximately 1.5. So this one's a bit more of a lengthy question. It pulls in a lot of concepts with each other. You need to know how to write equations, how to calculate moles, how to find your LR and ER, how to find your leftover ER, how to then use that leftover ER, your acid or base, make a dissociation equation, find the H plus moles, find the total volume, and then do your negative log of your hydrogen ions to get your pH at the end. Let's go make sure that we're on the right track with that. So we want to see if our answer was correct. So here we are. That was a challenge. We got about, that's right, 1.5. So it is acidic in the end. So we can write that down. Therefore, we are still acidic as a solution overall because of that excess HBr. It is a challenge, but it's a good one, and you'll see something similar to this in your lab. So I highly recommend you try that out. And you have to try this a few times, and you will get it eventually. I also want you to think, well, what if you had leftover base? How would you have found the pH, right? So think about what would have been different. If you had leftover base, everything would have been similar. But when you did your dissociation equation, you would have the OH concentration. You'd find your POH first, and then you'd have to do 14 minus pH or POH to find your pH in the end. So it does draw a lot of concepts together, and that's okay. It's difficult at first, but you will get it if you try it. There's another video here that I said was similar to that problem. So if you didn't already watch it, you can try that out and just retry this same problem over and over again until you get it. Watch the video until you get it. Make sure you see every single step. If there's a step you don't understand, go back in the lesson to see where that step came from so that you can comprehend every step. And that way you're not just memorizing, but you're also understanding all the steps, and you can do it for yourself next time there's a similar question like this. So that concludes all of the titration questions. Lots of calculations to try out. It does look like a short lesson, but there's a lot of concept there. It is heavy. So I do need you to go through the videos, especially where you see some models on how to do the lab. I want you to practice sketching, understanding what's in your burette, your titrant and then your analyte in your flask. So do understand this conceptually very well, because especially if you're planning on taking grade 12 chemistry or even biology in future years, you're going to be doing titrations. It's a very, very, very important skill. Once you master it, it's pretty straightforward. It's a basic skill. You'll really like it, but you do need to understand the concept. And your advantage is that you can master this theoretically right now, so that when you do go back to the lab, your theoretical understanding is going to be so good that the physical practice is going to be pretty easy to pick up once you get there.